So real numbers is the topic for the session. So what are real numbers? And what are the different types of numbers which we have already discussed in the lower classes, where we have studied each of different types of numbers like natural numbers, integers, and rational numbers, irrational numbers, etc. and etc. So these are all the numbers which we are going to discuss in today's session. So before we start with real numbers, let's start with a mapping diagram on what the different kinds of numbers are. Say for example, we know that we have natural numbers denoted by n, then we have whole numbers denoted by w, then we have set of integers denoted by z, and we have set of rational numbers denoted by q, and then we have finally the real numbers denoted by the symbol r, a Roman r. So these are the different types of numbers which we are going to discuss in today's session, mostly about the real numbers. Now coming to the natural numbers, we know that natural numbers obviously start with 1. The least of the natural number is 1 and the highest is undefined. It can be any big value, but initially it starts with 1. I have natural numbers as 1, 2, 3, 4 and so on and so forth till infinity. Similarly, when I start with whole numbers, the only difference out here is that it has an additional 0 along with the rest of all the natural numbers. So if 0 is included with the natural numbers, I get whole numbers in the form of 0, 1, 2, 3 and so on and so forth, this being the additional element. Next, I have the integers which start from negative infinity and accepting all the negative numbers in the form -3, -2, -1, 0, 1, 2 and 3 and so on and so forth. So these are the types of numbers which are called integers. Integers have both negative and positive numbers, including 0, which is neither positive nor negative. Then I have rational numbers, which is defined in the general form as p over q, all the numbers in the form p over q, such that it satisfies with two conditions. One is that p and q must be integers, and secondly, the condition is that q should not be equal to 0. So under these two conditions, all the numbers in the form p by q are called rational numbers. We're going to discuss about rational numbers more briefly out in case of this topic, but before that, let me also define the real numbers, which are given in the form of p by q such that q is not equal to 0. So what is the difference between rational numbers and real numbers? Rational numbers has the restriction that both the p and q, which are considered in the numerator and denominator respectively, must be integers. But in this case, p and q need not be integers. It can also be any number which is not an integer too. But in both the cases, the rule is that q should not be equal to 0, because any number where the denominator is 0 is said to be an undefined value. And hence, the restriction for both the set of number system is that q is not equal to 0. And this is how I define each of the sets of numbers in the real number system. Now to come more briefly with q, we call q as rational numbers. So what are rational numbers? More briefly, as defined here as p by q, such that pq belong to z and q not equal to 0. Let's take with some examples as a recap of already discussed topic in the previous sessions in the lower classes. So let's take some examples for rational numbers and see what type of numbers are rational numbers and what type of numbers are not rational numbers, as a recap from the already learned topics of the previous sessions. So for example, I take 4 over 5, then this is clearly a rational number because p and q, where p is 4 and q is 5, accepts the condition that p and q are integers, and q being 5 is not equal to 0 because 5 is clearly a non-zero number. Therefore, I can say that this is a rational number based on condition 1 and condition 2, under these two conditions of q. Similarly, let me take another example. Say I had taken 7 over 0. So in this case, this is not a rational number because 7 and 0 are integers, but q should not be equal to 0. But in this case, with this condition is failed. In case of the example, it's 2, 7 over 0. Similarly, if I take another example, say root 6 or root 5, then root 5 is not a rational number because if you take this in the form p by q, where root 5 can be written as root 5 over 1, then root 5 is not an integer. So p is not an integer. Therefore, this fails the condition of being a rational number. Similarly, if I take more further examples, say for example, I take root 4 by root 9. I wanted to test for this being a rational or an irrational number. So in case of this, I simplify further to identify whether this can be simplified more further. So let's see if we can simplify this. So we know that square root of 4 is 2. And we also know that root of 9 is 3. So that the simplified answer for root 4 over root 9 is 2 over 3. Thus, this satisfies both the conditions of a rational number, with 2 and 3 being integers and 3 not equal to 0. Is how I identify the two cases, and hence proudly I can say that root 4 over root 9 when simplified is a rational number. But the same problem, if I just take it in the form root 4 over root 3, then this is not a rational number because though I can simplify this to be root 4, which is 2, and this can be written as root 2 over root 3 because root 3 cannot be further simplified. Therefore, 2 over root 3 is the simplified part of this, but cannot be further simplified. This fails the condition of rational numbers because my first case says that p and q must be integers, but p is an integer, but q is not an integer because q is root 3.